Okay, so we're going to be looking at circular motion, all of it in as short of a time as possible. So without further ado, let's start. So what is angular displacement? That's going to be the angle through which the object has moved. We show it through the symbol of theta. Okay, and I hope you know the formula. S is equals to r theta. This is the formula that links the linear displacement s with the angular displacement theta, and then we have r as the radius. And the units we use for the angular displacement are going to be radians. So 1 radian is defined as the angle subtended from the center of a circle by an arc length equal to the radius of the circle. Alright, then if you take this equation, omega is equals to change in theta by change in t. This is the angular velocity. The angular velocity is defined as the angle swept out per unit area by a rotating object. It is measured in radians per second. And then we've got the frequency, the number of complete revolutions or cycles per second. It is measured in hertz. The time period is the time taken for one revolution or cycle, and we have it in seconds. So we've got the angular velocity is equals to delta theta over delta t. It's also equal to 2 pi over capital T, which is the time period. And we can also write it as 2 pi f, where f is the frequency. So these are the formulas that you have. One more formula. So S is equals to r theta. If you divide this equation by t, you're going to get V is equals to r omega or omega r. That's the other equation that we got. So most of the questions that you get from this content is very easy. So we've got a question here. We have got these children playing on a roundabout, and the roundabout is flat, platform with bars, and basically the children will rotate it. It takes 12 seconds for a roundabout to make 2 complete revolutions or rotations. A child is standing on a platform 1.8 meters from the center of the circle, so that's going to be your radius. So we need to find the speed. V is equals to r omega. R we know, we have to find omega. So 12 seconds for 2 complete revolutions. So 1 revolution is going to take us 6 seconds. So we can say omega is equals to 2 pi by t. The time period is the time taken for 1 revolution, so that's going to be divided by 6. So we're just going to plug this in the original formula now. We can write 1.8 times 2 pi over 6. That's going to be 1.88 meter per second. Next, we have a lot of important points I want to talk about. First is the speed versus velocity in the uniform circular motion that we got. Now, speed is the rate of change of distance, and in uniform circular motion, the object moves with a constant speed, right? Only the direction of motion changes. So the speed is going to be constant. Now remember, velocity is a vector quantity, so it depends upon the speed and the direction. Even though the speed is constant, the direction is continuously changing, and therefore the velocity is continuously changing, and there is centripetal acceleration towards the center of the circle. If there is a change in direction, that means that there is a resultant force. Okay? So remember this point. Okay. Next, we're going to talk about the work done and kinetic energy. The speed remains constant in uniform circular motion, so the kinetic energy, which is dependent upon the mass and the velocity, it also stays the same. Now remember, in uniform circular motion, the centripetal acceleration is going to act towards the center of the circle, and the force, the centripetal force, is perpendicular to the direction of motion. So this is going to be the velocity at this point. Let's say this is point A. So this is going to be the velocity, this is going to be the force, right? So every point if we take on the circle, the force will always be perpendicular to the direction of motion. Okay, and if they are perpendicular, that means the work done is 0. Okay, so there is no change in the kinetic energy as well. That's evident because the kinetic energy is constant. Okay, and then the work done is FD cos theta. Theta here is going to be 90, is the angle between them, and cos 90 is going to be 0, so work done is equals to 0. Okay, so I hope this point is clear as well. Next, we're going to finally talk about momentum. Momentum is a vector quantity. The magnitude of momentum remains constant because speed is constant. The direction of momentum continuously changes, so momentum is constantly changing as well. All right, so these are going to be the 3 points that you have to think about and know for the exam. Now we're going to be talking about centripetal acceleration. Now this type of question comes up a lot. I'm not really going to be reading it. I think since you are revising, you should expect you should know this. So let's say the object that we got here moves from A to B. Okay, so velocity at A, VA, and then we've got velocity at B, VB. Okay, so velocity at B, and then we've got velocity at A. All right, so change in velocity is equals to velocity final minus velocity initial. That's going to be VB minus VA is going to be delta V. All right, so delta V plus VA, velocity at A, is going to be velocity at B. That's the equation that we got. Now in these type of equations, remember, these are vector equations. These are going to be your components. This is going to be the resultant. So we've got this as the components, and this is going to be the resultant. Okay, right, so this is going to be VA, and this is VB. All right, and then we're going to put here change in V. All right, so let me just draw it a bit better, and something like this. Okay, change in V, VA, VB. We can see that these are the components and this is the resultant. So I hope this diagram is clear. It's very important you draw this. There are marks for this. Okay, that's the first part of the question done. Okay, now I want to look here back at the diagram. So we've got our triangle over here, theta. This is going to be R, this is going to be R, and this is going to be delta S. And let's instead of calling it theta, let's call it delta theta. I think that would be better. Delta theta. Okay, now what we have done here is we're going to assume that our delta theta is so small that our change in S is a straight line. Okay, our delta theta is so small. So we're going to take it so small, we're going to make this so small that this arc length that we got is a straight line. So we can take it as a triangle. Right, so that's how we get the second triangle now. Okay, now notice here, the angle is between the 2R and then the change in S. So angle here must also be right over here. The change in theta must also be here, because both of these are going to be VA, VB, and then we have the change here as well, the change in V. Okay, now VA and VB are going to be equal in magnitude. Now after drawing these two triangles and saying that VA is equal to VB, we can use similar triangles to say that delta theta is approximately equals to delta V over V. And the reason I can say that is because delta theta is going to be equals to delta S over R. Okay, now from here what we can say is that we know delta theta will be equals to omega times delta T. So I can say omega times delta T is equals to delta V over V. And we know V is equals to R omega, and omega hence is equals to V over R. So I can get rid of this and write V over R times delta T is equals to delta V over V. Then I can take the time to the other side and this velocity to the other side. So I'm going to get V squared over R is equals to delta V over delta T. And we know delta V over delta T is going to be the centripetal acceleration that we're going to have here. So I'm going to get the centripetal acceleration as V squared over R. I hope this is clear. Now I'm going to show you the mark scheme. So the centripetal force is F is equals to mv square over r, and F is equals to mr omega square, right? So we've got a question here, we'll just quickly do it. A model airplane is attached to a wire. The wire is held by a person as shown. The airplane moves in a horizontal circle like this, of radius 28.5 meters at a speed of this much. A lift force acts vertically upwards on the airplane. The lift force is equal to twice the weight of the aeroplane. And then it says the mass of the aeroplane is 1.55 kg. The wire will break if the tension is greater than 35 newtons. Deduce whether the wire will break. So first of all, let's see the forces. So we've got a lift force here. Lift force, we've got weight, and we've got right over here the tension. We're going to have angle theta right over here. Okay, I'm going to draw a free body diagram. So the lift force is twice the weight. So it's going to be 2W, W, and then we've got theta. And we've got the tension there. Okay, now what I'm going to do is I'm going to add both of these forces. They're in opposite directions. So it's going to be 2W minus W. And we're going to end up with our diagram looking something like this. W, tension here, and theta. Now what I'm going to do is I'm going to make components of the tension. So this is going to be T cos theta, T sine theta. Now the plane is moving in a horizontal circle. It's not moving up or down, which would mean that these two forces are equal to each other. It doesn't have a vertical motion. Okay? And then this T cos theta is going to be your centripetal force. So T cos theta is going to be mv squared over r. And then we got T sine theta is going to be equals to mg, the weight basically. Alright, now I'm going to take both the equations. We're going to divide them, and we're going to get tan theta is equals to mg over mv squared over r. These two m are going to cancel out. We're going to get tan theta as this is going to move up, so rg over v squared. Okay, I'm going to remove this. So now we're going to get our theta value. Theta is equals to tan inverse of 28.5 times 9.81 or 22.5 square. That's going to be 28.91 degrees. Okay, now we go back to the original equations that we had. So we're going to just plug it in here. So T is equals to mg, that's going to be 1.55 times 9.81 over sine 28.91. That's going to be 31.4 newtons. So 31.4 newtons is less than 35 newtons, so it is not going to break. Okay, you can write the conclusion down. Now that's the first way of doing it. You can do it another way as well. So remember we had a force here. That was the lift force, so that's going to be W, and then we have this force, theta, and then T here. Okay, so I'm going to take this back like this. We're going to have this as a theta, so we're going to have this. One second, let's put the arrows here. This is going to be the tension. This is going to be the lift force, which is equal to the weight, and this is going to be centripetal force, Fc. This is the resultant force basically. Okay, and then this is going to be theta. So you can calculate the resultant force, mv squared over r. Okay, you get the resultant force. You have the weight already, and you can use Pythagoras theorem, w squared. This is going to be the hypotenuse, right? So w squared plus the centripetal force square is equals to the tension. You can do that as well. Now let's talk about this question right over here. It says when a car was traveling at high speed around a circular path, I was thrown outwards due to a force acting on me. The upward force acting on me was the centrifugal force. Assess the claim made by the passenger. So first of all, according to Newton's first law, if no force is acting, no resultant force is acting on an object, it will keep moving in a straight line path. Okay, but we can see this object is changing directions. It's not moving in a straight line path. Because of this, what we can say is because the car changes direction, there must be a force. There must be a resultant force. And that resultant force is going to be the centripetal force that's acting towards the center of the circle. Okay, so that's going to be the centripetal force that acts towards the center of the circle. And because the car is experiencing the centripetal force, the person will also experience the centripetal force. And because of this, what we can say, remember always to say whether this claim is correct or not. So this claim is wrong because there is no outward force acting on the person. Alright, so here we have it. So Newton's first law states that if an object continues in a straight line at constant velocity, unless acted on by a resultant force, if centripetal force becomes zero and is not sufficient, the object will move in a tangential path. Very important for exam point of view. Some questions asked this as well. Okay, remember when you remove the centripetal force, the object will move in a straight line path. Okay, and then this we already discussed. You can pause the video and read through this, right? So this is going to be no resultant force. Okay, you put that arrow, no resultant force, and this is going to be, yes, there is a resultant force. Okay, I hope that's clear. So this is going to be the answer to that question. All right, so you can talk about the direction and the force, and then the force acts towards the center of the circle, and the inward force is exerted by the car on the passenger. So there's no outward force on the passenger, and his claim is incorrect. So all of this stuff, hope that's clear. You can check out the examiner report here as well. Now let's talk about one more example here where we've got the object moving again and they tell us to derive some stuff. So we've got this plane that's moving at an angle theta. We've got the thread, and it tells us that the forward and backward forces are on the toy are equal in magnitude. Add a diagram to show the other forces acting on the toy aeroplane. So it's going to be the weight, and then we're going to have the tension here. And then it says show that the angle theta of the thread to the vertical is given by this. So we've got this tension, we've got the weight, and you can see that these two angles are going to be the same thing. Okay, these are alternating angles. So this is going to be theta. So this can be t cos theta. This will be t sine theta. So t sine theta is going to be the centripetal force. T sine theta is equals to mv square over r. T cos theta is going to be equals to w. Both of them will balance out. So the object will not have any vertical motion. Divide both the equations, you're going to get tan theta mv square over r over mg. This cancels out, and we'll get tan theta equals to v square over rg. The final part, calculate the time taken for a toy aeroplane to complete one revolution. We're going to use the formula omega is equals to 2 pi by t. We need to find that t right over there. So we're going to use tan 22 over v square over 21 times 10 to the raised power of minus 2 times 9.81, and we'll find the value of v. So we're going to get the value of v as 0.91 meter per second. V is equals to r omega. V over r is equals to omega. So omega is going to be 0.91 divided by 21 times 10 to the raised power of minus 2. That's going to give me 4.34 rad per second. So I'm going to plug it in here. 2 pi over 4.34. So you're going to get an answer of 1.44 seconds. So you can write the answer as 1.4 seconds. Now we're going to talk about the vertical circle with tension / normal contact force. It depends. Sometimes tension, sometimes normal contact force or reaction force. It depends on the question. So here what I'm going to do is I'm going to answer all of these three questions. Okay. So we're going to be finding the equation at the top and bottom of the circle, and then we'll have to find out where the reaction force the normal contact forces maximum and minimum. Alright, so I'm going to take into the circle as positive and out of the circle as negative. So when we're at the bottom, we're going to have the normal force, or let's say the reaction force R here, and then we're going to have the weight acting down or out of the circle, that's better to say, and the reaction force will be acting into the circle. At the top though, let me make some space here, we're going to have both the weight and the reaction force acting into the circle. Alright, so at the top we're going to have the equation as both are acting inward, so R plus W is equals to mv squared over R. And then at the bottom you're going to have the reaction force acting into circle minus the weight is equals to the centripetal force. Centripetal force is constant, remember. I'm going to make the reaction force the subject in both of the formulas, and we're going to get these as the equations. This is at the top, this is at the bottom. So you can notice, it's actually the other way around, my bad. This is at the bottom, this is at the top. You can notice at the top we're subtracting weight, and then at the bottom we're adding weight. So reaction force at the top will be minimum, and at the bottom will be maximum. So it's going to change. So read this very carefully. A rope is tied to a bucket filled with water. The bucket is swung in a vertical circle of radius 1.2 meters. What must be the minimum speed of the bucket at the highest point of the circle if the water is to stay in the bucket throughout the motion? So at the top, we're going to have our forces. We're going to have the reaction force. You're going to have the weight force. So we're going to write weight plus the reaction force is equals to mv squared over R. Okay. Now, at the top, there will be a point, okay, where it is possible for the reaction force to be equals to 0, right? When this reaction force is 0, we're going to have V as minimum, right? So this is going to be the minimum velocity for the object to stay in that, for the water to stay in the bucket in the circular motion. Now, if R is greater than 0, then what's going to happen is that W plus R is equals to mv squared over R. And when you have the reaction force there, the velocity is going to increase, okay? So V minimum is when the reaction force is equals to 0. That's the minimum velocity, just so that we can complete the circular motion. Beyond that, if we increase the velocity, there is going to be a reaction force. So it kind of helps us out by increasing the velocity, and then we can comfortably move in the circular path. But for the minimum, when you're calculating, R is going to be equal to 0. So then we're going to have mg is equals to mv squared over R. This cancels out. So we're going to have v squared, right? Let me write that, minimum. So v minimum is equals to square root g over R. Okay. So we can see the minimum velocity is dependent on the radius of the on the square root of the radius of the circle. All right. So let me just plug those in. So square root 9.81 times 1.2. So we're going to have 3.43 meter per second. Let me just erase all of this. I have some 2-3 more points just to talk about here. Okay. So this is going to be the minimum velocity. So let's say we have velocity v and it's equals to 3.43 meter per second. And this velocity v is the velocity of the object that's moving in the circular path. So this is going to be enough velocity for us to move in the circular path. So this is just bare minimum enough to maintain circular path. Now, if our velocity is greater than 3.43 meter per second, then we can move in circular path. Okay. Now, if our velocity is less than 3.43 meter per second, then we cannot maintain the circular path. Alright, so I hope this is clear. That's going to be all for the summary of this chapter. Again, summary doesn't tell you everything, it tells you the essential things. So I'm only giving you a revision. Alright, if you want to go deep into the concepts and stuff, then better go with your lecture notes or with your teacher and stuff. So yeah, so this is just a revision for you to recall the stuff. Alright, that's all. And thanks for